We're recording. For those of you listening at home, we are going through homework 7D as in Douglas, page 421 and beyond. You can get on screen so you can see me. And there's 15 through 45 multiples of 5, 46, and then 49 and 50. And let me grab my glasses and see what we get. Here we go. Number 5, I believe, on page 421-ish. Oops, lost the page. There we go. Page 421, number 5. What is the solution of number 5? Where did they put it? Oh, they said which of the 3 methods would work. Pretty much any of them would work. Number 5, graphing is actually not all that bad. Substitution's not too bad because you can get a variable by itself pretty easily. 3 of them are pretty easy to get. Or you could do elimination by multiplying the bottom row by -1.
We started that question 15.
Well done. I'm blind. Yeah, sorry. I didn't see the 1 there. Number 15, forget I said that. That was like an infomercial. Choose a method to solve, explain your choice. You could do any of them. I would suggest substitution would be easiest because you could get x by itself pretty easily on the top and then just plug it in. Number 20, the actual solutions. X equals 3, y equals 3. Number 25, x equals 2, y equals -1. Number 30, again, this would be easier if you multiplied everything by 10 first and got the decimals out of there. You don't have to. X equals 16, y equals 14. And repeat stuff another bit. All right, number 35. This is where the answers start getting a little weird. X equals -3/4, and y is equal to 7/2. Number 40, x equals 2, y equals 3/5. Number 45, x equals 2, y equals 6. And it repeats. All right, number 46. You would need 4 8-inch pots and 2 10-inch pots. Number 49 and number 50. Number 49, how many children do you have to invite for the cost to be the same? 4 children. How many children do you have to invite for the cost to be less at the pizza place? More than 4 children. And it repeats on the whole thing. All right, questions? Any of those who want to see dissected yet? Yeah. Number 15, definitely. So picking a method, -3x equals 36, you could have done another method. You just have to give an explanation as to why. Let me see if I got a better marker. And then the other one was -6x plus y equals 1. Now again, could you do elimination? Yeah, you could. In order to do elimination, you'd have to fill in the rest of this. Look at the top row for a second. How many y's do you see? It's not a trick question. 0. That's exactly what you'd have to do. -3x plus 0y equals 36. And then you'd have this one, -6x plus 1y equals 1. Does that make sense? In order to use elimination, you have to make sure things line up. And the top one I'd multiply by -2. Because, why didn't I use the y's here? There's a specific reason. And normally you can do either what you want. I would say don't use the y's here. Yeah, good luck on getting this one up to -1. I'll multiply it by 10. It's still 0. I'll multiply it by -1 billion. Yeah, it's just dead. So this will be +6x plus, I was going to say -0y, but yeah. and equals negative 72, and then you can do 6x plus 1y equals 1, and just go from there. Does that make sense? You didn't actually have to solve it, you just had to pick a method and explain. I picked substitution because the top one is pretty easy to get by itself. Divide by negative 3, and you get x equals negative 12, and you're half done with the problem already. Then all you do is just plug that into x and get the rest. Does that make sense? Again, you could do either or. Graphing, I wouldn't. I mean, could somebody? Yeah, if they're super duper accurate. But this is going to be awkward. You could graph it, you can get it in slope-intercept form as y equals 6x plus 1. If you add 6x to both sides. That's not too horrible to graph, but trying to find out where these cross, you'd need a big piece of paper, and it gets a little hairy. So you could. I would say graphing is hardest, elimination is reasonable, and elimination is, and substitution is probably easiest. Next. Any other ones you want to see under the scalpel, so to speak? Does that make sense? So at this point, what I'm probably going to do, just so you know what's coming up on the test, people ask, do I have to use a particular method? I would say once. Like problem number 3 might say, solve this by graphing, no credit for other methods. And that's the only problem I'll ever do that with. Then problem number 4, solve this by substitution, no credit for other methods. Problem number 5, solve by elimination, no credit for other methods. And then I'll give you like 4 or 5 of them saying, solve any old way, please. Does that make sense? So most of them, it's going to be choose your own method. Choose the one you like best, and then go for it. Does that make sense? Any other questions on this one? Now's a good time to ask. Anything that would still be mysterious if I put it on the test? Going once. Twice and a half. I made that up. All right. All right, take out your notes. Let's finish off what we were talking about the other day. I do want to finish, in the last chapter test, we had we compared 2 lines. We wanted to see if they were parallel, perpendicular, or none of the above. I want to add 2 categories today. When you're comparing or solving 2 lines, there are 4 possible things that could happen. When you're solving, interestingly enough, it doesn't care if they're perpendicular or not. Solving could be, well, for example, it could be what we call regular intersecting. In other words, they cross once. And again, if you have 2 lines, that's not much of a surprise. They usually intersect once. There are 2 exceptions to this. Can we name them? When can you have 2 lines that do not cross once? Parallel. How often do they cross?
Sometimes.
Correct. These never cross.
Can also be lines that cross more than once.
Interesting. We'll look at that in a second. These, in geometry, there's a special symbol we use for parallel. The symbol for writing parallel looks like this. It looks like 2 slashed lines. But when you're actually doing a diagram, if you want to show the 2 lines of parallel, do this. Have identical number of arrows pointing the same way. This implies parallel. You don't have to use 2 arrows. You could use 1 arrow each. whichever you like, as long as they match. Okay, and we gave a quick hint on this last week of what it looks like. If you're solving a system and you come up with parallel lines by accident, what does it look like? I'll ask in a moment. There's one, that's the question. Can two lines ever cross more than once? Like what?
Or they go like this, and if there's like.
Oh, interesting. However,
They're not
there's one
lines.
catch. That would no longer be a line. A line has to be straight. You're right, by the way. If you have a bendy thingy, we call it a curve. If a curve hits a line, you could probably hit twice, or even 3 times if it's psychotic, or a billion times if it's completely hiccuping forever. If you have 2 straight lines, can they ever cross more than once? You think the answer is no. And you're right in a certain sense. But there is one exception.
Well, if they're on top of each other.
Yes. If you have 2 lines that are on top of each other, how many times do they cross? An infinite number of times. It's all over the place. They're crossing an infinite number of times. Now, what we were thinking of, can 2 lines cross like 5 times? No, they can't. They can either cross 0 times, 1 time, or infinitely many times, and those are the only options. This, by the way, is called coinciding lines. In other words, they cross an infinite number of times. They're on top of each other. They're the exact same line. Okay. And those are the only 3 as far as solving. Now in number 1, there's a category of number 1 called perpendicular. If you're solving a system and they say, hey, they cross once, is that enough to tell you if they're perpendicular or not?
Yes.
Like I say, here's 2 lines, I know they cross at one point.
No.
No, they could be tilting this way, they could be perpendicular, they could be like this. Is it enough to tell you that if they're parallel or not? If I say they cross once,
If they're parallel.
if they're parallel or not?
Yes.
Yes, that you can figure out. If they're crossing once, parallel is disqualified. If they're crossing once, you don't know if it's perpendicular or not, because perpendicular depends on the angle they're crossing at. So here, in this particular section, we're not too worried about perpendicular. It'll come back for the chapter test. But for now, the main 3 are regular intersecting, which means perpendicular is a type of that, where they cross once. Then parallel is where they cross 0 times, and coinciding is where they cross forever and ever, amen. Every single place along the line. Make sense? So what does that look like? We've actually run into this before. Quick example. 3x plus 2y equals 6, and negative 6x minus 4y equals negative 12. I'd like you to solve that. What method do you think would work best on this? You could do any.
What's that called? It's, you multiply one of the.
Yes, that's a type of, there's graphing, substitution, and elimination.
Elimination.
Elimination. What's the secret to elimination? You're trying to get what? Hence the name.
Oh my goodness, that just all been on me.
Maybe. What are you trying to do? You're trying to get something to cancel out. Yeah, cancel out. So take a pick. You want the x's, the y's? Yeah, I know it's a trick. Yeah.
Why?
The y,
Cancel.
sure, sounds good. The y's cancel. How do you get the y's to cancel? They're not quite canceling it. Multiply the top by 2. Correct. Let's do it down here. So 6x plus 4y, and make sure you multiply the other side also. 12. And then this is negative 6x minus 4y equals negative 12. All right, add them up.
Everything cancels out.
Yep, and then do. Now you have to write something.
0.
The equal sign is still there. What's that?
0.
0 equals,
0.
yeah, congratulations. It's kind of like, I'm going to tell you one of the great secrets of mathematics. Is everyone paying attention? 0 is equal to 0. Professor, question? What does that mean? Well, it means that 0 is equal to 0. We kind of knew that. Is there any new information in here? Everyone wants something new. What about, yeah, you get the idea. There's no new information about this. 0 is equal to 0, of course it is. You know, we lost something. All the x's and the y's died. We want to get one of the variables to cancel so you can get the other one solved. Well, this one, they both just got wiped out, so well, that's awkward. But what does this mean? The question is, whenever this is true, the two lines cross. That's going to be true in any solution ever, forever and ever, all the way up through calculus. If you have two graphs, like whenever this at the solution is where they cross. Where do these cross? Any ideas? Like whenever this is true, the two lines cross. How often is this true?
All the time.
All the time. How often do the two lines cross? All the time. Guess which one we're talking about? We're talking about coinciding lines. So I'd like you to write the word coinciding. That would be your answer on this problem. Coinciding. Like wherever the two lines are, I don't even know. You could graph them to find out. They're coinciding. They're the exact same line. Does that make sense? What if you got a solution where I'm just going to make up something, you know, blah 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 blah, and then you solve. People watching at home, I was going to say don't try this at home, but yeah, feel free to try this at home. You'll just get a weird answer, and you get something like 0 is equal to 5. What does that mean? Whenever that's true, the lines are crossing. Like whenever the solution is true, the lines are crossing. How often do actually, maybe, how often is 0 equal to 5?
Never.
Never. How often are the lines crossing? Same answer. How often is this true?
Never.
Never. So how often do the lines cross?
Never.
Never. What kind of lines are we talking about? What group of lines would never cross each other? Which of these three? What's that? Parallel. This, as your answer on the test and on the homework, you'd write the word parallel. Questions so far? Does that make sense? If you actually get a solution, like x equals 2 and y equals 5, that's the intersection point, 2, 5. Does that make sense? So they're going to be asking you, where do these two lines cross? And you're going to put either a point, 10, 3, or you're going to put parallel, or you're going to put coinciding. Now, a couple of cautions. What if they do this? I've seen this happen. This really, like, once you see it, it's obvious, but before you see it, this just, it's like somebody dropped a brick on your head out of orbit. It's, what? Here's the system for you. X equals 2, y equals 3. I'd like it solved. Can anybody tell me, are they regular intersecting, parallel, or coinciding? Why do you say regular?
Because it's only one point.
Where are they crossing? What comma what?
2, 3.
Yeah, they give you the answers already, it's done, which is totally funny. 2, 3. If you want it proved, x equals 2 is a vertical line. This is x equals 2. And the y equals 3 is a horizontal line. And look where they're crossing. 2, 3. It works. In other words, if they give you a goofy answer, just give them a goofy answer back. What if I said x equals 2 and x equals 3? What do you think? What kind of lines are we dealing with? X equals 2 and x equals 3. You're close. Parallel. X equals 2, x equals 3. One space apart. X equals 2 and x equals 2, ding, 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 coinciding. Oh, let me show you a sneaky one. seen this before. X equals 5 and 2x equals 10. What kind of lines are we talking about? Coinciding. Why do you know? Why do you say that?
Because you have to simplify.
Yeah. If you divide this by 2, you get x equals 5. Does that make sense? Righty. Good look. Let me put the, okay. Isaiah, I'll be right back to put the assignment here. I'm just going to put it on the sideboard. I'll read it off in person. I don't know. Has everybody watched any of the videos that I put on? I didn't put many in this class, so, and I don't think you really needed to. But I was just curious if the sound quality was enough to hear me properly. Whatever. I'm looking on page 429 and following. So page 429, I would like you to do numbers 1, 2, and 3. I would like you to do 12 through 17. Actually, hang on a second. Yeah, 12 through 17. 19 through 29 odd. Let me just put that down below. And I think there's one more. Hang on a second. And then number 30. And that'll be it. All right. Let me recopy this on the front board. People in here, you can go ahead and just get busy. I'll put the thing up for Isaiah. And so, I'm sorry.
You would probably just turn the iPad so I could see it on the other board.
You can tell I'm not an engineer. That's brilliant. Just a second. You know when it's in pre-calc, there's a point where you have to like take a graph and rotate it 90 degrees. And I was trying to do this on the board. There you guys, yeah, you can thank Mr. Dugan for actually thinking of that, where your teacher did not. So 7E, page 429 and following, 1, 2, and 3, 12 through 17, 19 through 29 odd, and number 30. Good to go? And yeah, I'll keep this on while I finish the story. You're supposed to rotate a particular graph 90 degrees, and I was having a fit doing it on, doing it on paper. And then saying, what does it look like? And you know what somebody suggested? Said, because I was like turning my head 90 degrees and getting a crick in my neck and such. And so we said, do you ever think of like rotating your book 90 degrees? No. It worked like a charm. So anyway, take care. Talk to you later. This is my hand webbing. Bye. Bye-bye.